In last video, we proved questions up to 7. Now, let's jump to the next question. I think we have already proved this type of question. Example 11 is similar to this question. The only difference is divisor. Here we have 5 and we have 6 in our question. So do it by yourself. Okay, let's see next question. This question looks different, but don't worry. We have already proved this question. But let me fix some issues. We have been asked that the cube of a positive integer will always be of the form 6q plus r, where q is any integer and also r is 0, 1, 2, 3, 4 or 5. That means we have 6 reminders. So 6q plus r will have 6 forms. In these 6 forms, we will change r by given reminders. I think this question is now much more clear. That means the question is, prove that the cube of a positive integer will be of the form 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 or 6q plus 5. Now look at example 7. This is quite similar to our question. Also example 6 is similar to our question. So we will have 6 cases. You will have to prove each case one by one. Let's see example 10. We have already proved this type of question. Question 4 is similar to our question. Also example 12 and example 13 are similar to this question. So do it by yourself. I want to repeat that if you find any difficulty during calculations, you can tell me. I will make another video on this topic. But some student may ask why I am not proving these questions. And if you are thinking about asking it, then you are not a math student. You are just kidding. I can prove each and every question, but you won't learn anything. I have covered each and every type of questions related to this topic. Now it's your turn. You have already understood basic and advanced questions, and still you can't solve these questions. Tells only one thing. You are just studying class 10 to pass the board exams, not for learning. You are a fake math student. So don't ask this question and do these questions by yourself. Okay? I think it's enough for you. Let's see question 11. These type of questions have been proved earlier. Question 5 is similar to our question. That means example 4 is also similar. So do it yourself. Let's see next question. I think this one is different from all other questions. Question is, a positive integer is of the form 3q plus 1 and q is a natural number. And natural numbers start from 1 and go up to infinity. So what is our number? Let's find it out. If we take 1 in place of q, we get 4. If we take 2 in place of q, we get 7. If we take 3 in place of q, we get 10. If we take 4, we get 13. So we have these numbers. In the question, we have been asked to take squares and see whether its square is in the form 3m plus 1 or 3m or 3m plus 2 or not. And also we have been told to justify our answer. That means you have to check the answer by yourself and then you have to tell your answer. So the given positive integer is of the form 3q plus 1. All these 4 numbers are of the form 3q plus 1. So let's take their squares. 4 square is 16, 7 square is 49, 10 square is 100. And 13 square is 169. 16 can be written as 3 into 5 plus 1. 49 can be written as 3 into 16 plus 1. 100 is 3 into 33 plus 1. And 169 is 3 into 56 plus 1. Now you can replace these numbers by m. And you can see we get only one form, that is 3m plus 1. So what that it means? It means 3m and 3m plus 2 are invalid forms. That means the square of 3q plus 1 will always be of the form 3m plus 1. It cannot be 3m or 3m plus 2. And that's why we have been told to justify our answer. But in question, we have been asked, can you write its square in any form other than 3m plus 1, 3m or 3m plus 2? And we found out that this statement in the given question is not acceptable. 3m and 3m plus 2 are wrong forms. Only 3m plus 1 is right one. But we have to prove this question on paper, because till now we have only understood the meaning of this question. So let x be a positive integer and x is equal to 3q plus 1. We have taken a square of 3q plus 1, that is 9q square plus 6q plus 1. From these two terms, 3 can be taken as common and we get 3 into 3q square plus 2q, and plus 1 can be written as it is. This whole term inside brackets can be assumed as m, where m is some integer, and we get 3m plus 1. Hence we can justify our answer by saying that The square of a positive integer which is of the form 3q plus 1 will always be of the form 3m plus 1. It cannot be of the form 3m or 3m plus 2. Let's see next question. I think this question is familiar to you. You have already proved such questions. Example 11 is similar to our question. Let's see next question. I think this question is little bit tough. And the formula to solve tough questions is very simple. That is, understand the question completely and then try to solve it. We have two positive integers a and b such that a is greater than b. So we can take some integers such that a is greater than b. And we have a plus b by 2 and also we have a minus b by 2. If a plus b by 2 is odd, then a minus b by 2 is even. And a plus b by 2 is even, then a minus b by 2 is odd. That is the whole summary of the given question. But how to start solving this question? First of all, let's check whether this question is right or wrong. 9 plus 7 by 2 is 8 and 9 minus 7 by 2 is 1. Again, 23 plus 13 by 2 is 19 and 25 minus 13 by 2 is 6. And 47 plus 11 by 2 is 29 and 47 minus 11 by 2 is 18. Now 8 is even and 1 is odd. And 19 is odd and 6 is even. And 29 is odd and 18 is even. So it is clear that if a plus b by 2 is even, then a minus b by 2 will be odd and vice versa. I think we have understood the question very well. Let a is equal to 2m plus 1 and b is equal to 2n plus 1. This is happening because a and b are odd integers. And that's why we have taken a is equal to 2m plus 1 and b is equal to 2n plus 1. And also m is greater than n because a is greater than b. A is greater than b is given in the question. That's why we have taken m is greater than n. But why we are taking m as greater than n? So if we take m is equal to n, then 2m plus 1 and 2n plus 1 will become equal. That means a will be equal to b. That means our statement a is greater than b will be declined. That's why we are taking m is greater than n. Let's go further. So we have a plus b by 2. That means a is 2m plus 1 plus b is 2n plus 1. Now we can arrange them. Also by dividing the whole numerator by 2, we get m plus n plus 1. Also we can write a minus b by 2. Here a is equal to 2m plus 1 and b is equal to 2n plus 1. So they will be inside brackets because we have minus sign in b. So we can shift negative sign inside brackets. Plus 1 and minus 1 will be 0. So we get 2m minus 2n by 2. By dividing this number, we get m minus n. Now a plus b by 2 is m plus n plus 1. And a minus b by 2 is m minus n. But how do we prove our question? We know that a and b are odd positive integers, but a plus b by 2 is not clear whether it is odd or even. Let me bring our previous example. Here you can see 8 is even and here 1 is odd. But what about m plus n plus 1? Is it odd or even? And what about m minus n? Is it even or odd? But why we are finding them? Can't we solve this question without knowing what they are? First, let me clear this confusion. Here by seeing these numbers a plus b by 2 and a minus b by 2, we cannot clear that whether they are odd or even. Also by seeing m plus n plus 1 and m minus n, we cannot tell whether they are odd or even. That's why we are searching for more information so that we can solve this question. A and b are odd integers because it is already given in the question. But what are m and n? I think they are just integers. It may be even and also odd. That means they are even and they are also odd. If m is 1, then 2 into 1 plus 1 is 3. If m is 2, then 2 into 2 plus 1 is 5. If m is 3, then 2 into 3 plus 1 is 7. If m is 4, then 2 into 4 plus 1 is 9. So here you can see a is always becoming odd integer, but m may be odd or even. So let's see a statement which is very useful to prove this question. Now we are taking addition of m plus n and we have some examples. Don't be panic. I know you are confused little bit, but your confusion will fade away in few minutes. So here 22 plus 5 is 27. 22 is even and 5 is odd. That means m is even and n is odd. In second example, 15 is odd and 7 is also odd. That means both m and n are odd. And in third example, m and n both are even. That means we have taken all possibilities that can happen. Here m and n are not sure whether they are odd or even. That's why we have taken all possibilities. And what are these possibilities? First possibility is both m and n are even. Second possibility is both m and n are odd. And third possibility is only m is even and second number is odd. That means we have taken all possibilities. Now let's see what is m minus n. So m minus n means 22 minus 5, which is 17, and 15 minus 7 is 8, and 8 minus 2 is 6. And it is the point where you are going to realize that you are on the right way to prove this question. I have taken m plus n because here we have m plus n, and also we have plus 1. And I have taken m minus n because here we have m minus n. Now observe this carefully. 27 and 17 are both odd integers. That means m plus n is odd. And also m minus n is odd. In second example, 22 and 8 both are even integers. Also in third case, 10 and 6 are even. That means both m plus n and m minus n are even. Now you can say by yourself, if m plus n is even, then m minus n is also even. If m plus n is odd, then m minus n is also odd. And now we can say the statement that we know the sum and difference of positive integers is either both odd or even. Therefore m plus n and m minus n both are even or both are odd. So we get two cases. Case 1. If m plus n is even, then m minus n is even. So a plus b by 2 is m plus n plus 1, and a minus b by 2 is m minus n. So see carefully. Here m plus n is even, and by adding 1 in even integer we get odd integer. That means m plus n plus 1 is odd. Also here m minus n is even. That means m minus n is even. And hence we proved m plus n plus 1 is odd. That means a plus b by 2 is odd. And m minus n is even. That means a minus b by 2 is even. And we proved our question for first case. Now let's take second case. If m plus n is odd, then m minus n is also odd. So we have taken case 1. This time m plus n is odd, and by adding 1 in odd integer we get even integer. That means a plus b by 2 is even. Here m minus n is odd. Therefore, a minus b by 2 is also odd. And you proved this question completely. This is the end of Euclid's division lemma. Now you can prove any question based on this lemma. Let's end this session. See you soon.